Hello everyone, it's Mrs. McCready here and I'm going to talk you through everything that you need to know for C12 chemical analysis for combined science. Just to start off with, there is a do now up on the screen, so your teacher's going to pause the video here and let you tackle these questions. Okay, we'll go through the answers to those in just a moment, but just to talk you through what we're going to cover in this session. We're going to talk about pure substances and mixtures and the difference between those two things. We're going to look at analysing chromatograms and calculating RF values. And we're going to look at the 4 gas tests that you need to know. Throughout this session, there will be opportunities for you to practice these skills and to look at the content in terms of exam questions. Okay, the answers to the do now are up on the screen here, so hopefully you managed to tackle those questions. These were simple mathematical calculations based on the idea of ratio, so if you're unsure about that, that's maybe something to go back and have a look at over the next few weeks. So we'll start this session by talking about pure substances and mixtures, the differences between those, and also some examples. So in everyday life, we often use the term pure, not in a chemical context. So you might talk about pure orange juice when you buy that from the supermarket. Now that substance isn't what we would call chemically pure, and you'll see why not in just a moment. So a pure substance is made up of just one substance. Now that can be an element or it can be a compound, but what's important here is that everything in that substance is just one type of substance. So for example, you could have something that is a pure substance made of an element, so this represents that. You can see all of the atoms are identical and we just have single atoms within that diagram. Our pure substance could also be made up of a compound. You can see in this diagram on the right-hand side, there are 4 molecules of a compound. This is still pure, even though we have 2 different types of atom here, it's still pure because it's only made up of that one type of compound. All the compounds in the box are the same as each other. And what's important about pure substances is they have fixed melting and boiling points, and this is one of the ways that we can test for purity. So for example, water will always melt at 0 degrees and boil at 100 degrees. So if we had a water sample, we could test whether it was pure water just by boiling it. If it boiled at a temperature anything other than 100 degrees, we would know it was not pure. When we talk about mixtures, they're made up of more than one substance, and you will have looked at mixtures throughout your education in chemistry. Formulation, though, is a new word to you this year, and a formulation is a specific type of mixture that has been designed to be useful. So, for example, paint, cleaning products, medicines, they all contain ingredients that are there for a purpose. So all formulations are mixtures, but not all mixtures are formulations. So for example, seawater is a mixture, but it is not a formulation because it has not been designed to be a useful product. When we think about the ingredients of these types of formulations, they're all there for a reason. So for example, in paint, you have a pigment which colours the paint. You also have binders to keep the paint together, and you have solvents to dissolve the pigment in the paint as well. So there's lots of different ingredients in formulations, but they're all there for a specific reason. The next thing we're going to talk about is analysing chromatograms. And you will have seen these before. They're essentially the pictures that we get from the chromatography experiments. You will have studied chromatography in C1 as one of our separating techniques for mixtures. But now in C12, we need to be able to perform some calculations to go alongside that. So you can see a very simple chromatogram up here on the screen, just of 3 different substances, A, B, and C. The way that chromatography works is it separates mixtures based on their solubility. So chromatography involves 2 phases. It involves the mobile phase, which is our solvent, usually water, and it involves the stationary phase, and that's our phase that stays still, usually paper. Now the different substances have different solubilities in the mobile phase, And the more soluble they are, the further they will travel up the paper. So that's how chromatography is separating out these different substances. If we don't know what a substance is, if it's an unknown substance, we can identify it by calculating its RF value. So that funny RF symbol stands for retention factor, and all it's telling us is how well it's dissolving in the mobile phase in chromatography. We can use a formula to calculate that RF value, and you can see it up here on the screen. So the RF value is equal to the distance moved by the spot divided by the distance moved by the solvent. I'm going to take you through a worked example for this one because sometimes it's a little bit tricky to see this on the diagram. So if our worked example had asked us to calculate the RF value of substance A, there's a couple of measurements that we're going to need to make. One is how far the spot has moved, and you can see that I'm measuring from the start line at the bottom to the middle of the spot A. The other thing I'm going to need to know is how far the solvent has moved. This time I'm measuring from the start line to the solvent front, which is where the solvent has reached at the top here. So those are my two measurements I'll need to know, and in an exam I would use a ruler to measure those two distances. I know this is my formula. The RF value is the distance moved by the spot divided by the distance moved by the solvent. And I just measure those two quantities from the arrows I've just drawn on my diagram. The distance moved by the spot when I measured that arrow is 2.1 centimetres, and the distance moved by the solvent is 6.2 centimetres. I pop those numbers into my calculator, I get an answer of 0.34. Now sometimes people will do this the wrong way round. Sometimes people will do the distance moved by the solvent divided by the distance moved by the spot. You'll know if you've got it the wrong way round because you'll have a number bigger than 1. The RF value cannot be more than 1 because the spot cannot move further than the solvent. So your number for your RF value should always be less than 1. If it's not, just check that you've done this calculation the correct way round. The final piece of revision that we're going to do today is on gas tests. Now these are qualitative tests that we can carry out to prove whether we've got a certain gas being produced in an experiment. The first test is for hydrogen. You can see in the diagram we have a boiling tube of hydrogen and we've got a lit splint being put into the bottom of it. The boiling tube is upside down, that's just so that the hydrogen gas doesn't dissipate into the atmosphere and that we get a better result. Now hydrogen is a flammable gas, and because it's flammable, when we put a lit splint next to it, we get a very small explosion, and that's what produces that squeaky pop sound. So a lit splint will give us a squeaky pop if we have hydrogen gas present. Next gas is oxygen. So again, we have our boiling tube here, this time it's full of oxygen, and we have a splint. The difference this time is that splint should just be glowing. It shouldn't actually be on fire, it should just be glowing orange. And the positive result is that because of that high concentration of oxygen, the glowing splint will actually relight and set on fire again. The third test is for carbon dioxide gas. And you can see here that the green arrow is representing carbon dioxide gas being produced in another flask or another tube and being bubbled into the test tube in the diagram. That test tube is full of lime water. If the gas is carbon dioxide, that lime water will turn cloudy. And the final gas is chlorine. You can see in the tube there is a solution generating chlorine gas. Now, if that gas is chlorine, it will bleach that piece of litmus paper at the top. So a piece of damp litmus paper will bleach and turn white if there is chlorine gas present. Okay, so let's look at the kinds of questions you might be asked about these 4 gas tests that I went through on the previous slide. Sometimes they'll be very straightforward and they will just say, describe the test for carbon dioxide gas or describe the test for chlorine gas, and you will know exactly what you have to do. Sometimes you'll need to do a little bit more work, and this is an example of one of those times. Have a look at this question. Hydrogen peroxide decomposes in the presence of catalase. This is the equation for the reaction. Describe how the student could test for the gas produced. Now you might be able to see this straight away, but if you don't know what the gas produced is, you're not going to be able to answer this question. So I need to go and look at the equation that they've given me to work out what the gas produced is. And what I'm looking for is the state symbol G. That symbol in brackets after the substance tells me what state that substance is in. And you can see that it is the O2 that has got the G symbol next to it. So that is the gas that's being produced. So I can decode this question as describe the test for oxygen gas. That's what this question is asking me. And then it becomes fairly straightforward. I know that the test for oxygen gas is a glowing splint will relight. And that's what I would write in my answer. Okay, we're just going to do 5 quick retrieval questions on the content that we've been through today. Your teacher's going to pause the video so that you can have 5 minutes to answer these questions on your own. And here are the answers so that you can review. A formulation is a mixture designed to be a useful product. The test for carbon dioxide is that lime water will turn cloudy. It would tell you that the water is not pure. If it was pure, it would boil at exactly 100 degrees. The difference between hydrogen and oxygen is that hydrogen requires a lit splint, but oxygen requires a glowing splint. And finally, that RF value cannot be more than 1 because the spot cannot move further than the solvent. So now we're going to look at 3 exam-style questions. This is the first one. Your teacher will pause the video here and give you a chance to read through and answer this question. When you're ready, they can press play and we'll go through the answer. Okay, so this question asked you for a little bit more detail than just the test for carbon dioxide. So they've asked you to describe how they could use the apparatus to investigate how long it takes for carbon dioxide to be produced. So we'll need the test, but we'll also need some sort of indication of time taken. So the answer to this question is that the student should time from when she starts heating to when the lime water turns cloudy. This is the second of our 3 exam-style questions, so once again, if your teacher pauses the video here and comes back when you're ready to go through the answer. So it's quite common for questions around formulations and mixtures to be phrased in a specific context, so like this one in terms of medicine. The first part, name given to mixtures like Calpol, they've told us in the question that it's a mixture designed for a specific purpose, and we know that that is the definition of formulation. So part A, the answer is formulation. The second part is asking us to suggest. Now suggest means that you need to use your own knowledge as well as what you've learnt through the course to form your answer. So suggest why colouring is added to Calpol. They've told us in the question that Calpol is a medicine marketed at children. So it would make sense that the colouring is added to make it more appealing to children or to make them more likely to want to take the medicine. So this is our final of the 3 exam-style questions. There are 4 parts to this question. You may need for the final part to ask your teacher to help you read off the values from the ruler if you cannot see in enough detail from where you're sitting. Once again, they'll pause the video here and come back when you're ready to go through the answers. Okay, so for part A, they'd asked how many substances are in the ink from the check. If I look at the column above the ink from the check, I can see there are 3 separate dots, which means there are 3 substances there. In part B, they'd said that substance B actually does contain 2 substances and asked me to suggest why there's only 1 spot above that substance. Now, sometimes substances have very similar RF values, and that means that they will travel a very similar distance up the paper. They may appear to overlap and appear just as 1 dot rather than 2. Part C, describe how chromatography separates the substances in a mixture. Now this is worth 4 marks, so we're going to need to use some key terms here. The substances dissolve in that mobile phase, remember that's the solvent, usually water, and they get carried up through the stationary phase, which is the paper. Substances that are more soluble will be able to be dissolved in the mobile phase for longer and be carried further up the paper before they can no longer dissolve in the solvent. And the final question, part D, you should have measured the distance moved by the spot as 3.3 and the distance moved by the solvent front as 6.7. When I do 3.3 divided by 6.7, I get an answer of 0.49. You might have read those numbers as something very slightly different. For example, you might have read as 3.2 or 3.4. As long as you've got around that answer, that will be absolutely fine. It's putting those numbers into the calculation that is important here. Okay, so that's the end of this video. Really well done. We've covered today pure substances and mixtures, the differences between those and the definition of formulation. We've covered analysing chromatograms and calculating the RF value. And we've also covered the 4 gas tests. Those are for hydrogen, oxygen, chlorine and carbon dioxide. If you've still got a bit of time left in this lesson, you should now use that to revise the concepts we've covered today.